Okay, so last time we gave kind of a start of graph theory, introduction to graph theory. Okay, so this was, well, we saw graphs and started talking about cycles, Eulerian cycles and Hamiltonian cycles. I actually want to go today to talk about a kind of a family of graphs where none of these exist. Okay, so these are called trees, which we've seen special cases of them before. Okay, so there's a couple ways to kind of define these or set these up. Let me do it this way. So a graph first is connected. Graph G is connected if every pair of vertices V and W in G, okay, so just vertices in G, is connected or are connected by a path. Okay. So what does this mean? You have, well, essentially the picture which you don't see is something like this, where you have a graph over here and a graph over here and no edges connecting any vertex over here to another vertex over here. So this is a disconnected graph. Okay? So you can ask if you have, say, a connected graph. So suppose there's a connected graph, so G is connected, and has n vertices. Okay, what's the minimal number of edges it can have? So what is minimal number of edges? Okay, of course it can have kind of the upper bound for the number of edges is, since we're not allowing double edges or loops, it's given to you by the number of edges in the complete graph, so n choose 2. And of course you can have graphs with 0 vertices, but they don't satisfy, or sorry, 0 edges, but they don't satisfy this connectedness condition. Okay, so let's just kind of see what the answer is. So the answer turns out to be n minus 1, and it's not too hard to see this. So if I take a graph with n vertices, imagine I just start off with the vertices without knowing what edges are connected. Okay. And now you start putting in the edges. Okay, so maybe I'll do this in a different color. So you start off with n components, so n different kind of vertex dots. Every edge that you add can connect, well, at most one or two of the dots together. Or you might make a chunk here and then start connecting it like so. But at every stage, you can only kind of fix up one new dot, which was previously disconnected from the graph and is now connected. Okay? So maybe let me write this out. So start putting edges. Each edge added makes at most one connection. Okay, so we started with n different components. We end up with 1. So if the graph is connected in the end, we need at least n minus 1 edges. Okay, and that's the minimal amount. So that we call such graphs trees. So a tree T is a connected graph. There are a number of different ways to define a tree, but is a connected graph with n vertices and n minus 1 edges. Okay, so if you leave off the connected condition, so a forest, which, is a pretty good name if something is a tree. A forest is a union of disjoint trees. So sometimes you want to consider graphs which might have a tree over here and some different tree over there. Maybe here's some more. Okay, so that would be a forest. Okay, and notice that every edge in the tree, so if it's removed, if removed, okay, disconnects the tree T. Okay, so in other words, if I look at the graph T minus E, where I don't delete the vertices of the edge, but I just say, well, this edge is no longer in here. This might be E. Okay, so every edge disconnects T just because, by the argument above, we need at least n minus 1 edges. Here we only have, n minus 2. Okay, so such edges are called bridges. Which I drew kind of a similar picture of for the case of Hamiltonian cycles. So this was an edge where if you had a graph over here and some graph over here, together it's a connected graph, but if I remove this edge, it becomes disconnected. So that's called a bridge. It turns out that an equivalent way to say this is that for a tree, well, so this is true, every edge is a bridge. It turns out also that if a graph G, and we'll see this in a second, if a graph G has every edge a bridge, it's also a tree. Okay, it is a tree. Should say connected here, sorry, connected. Graph G has every edge a bridge, it is a tree. So that's another characterization. So you can think of it either as this, let me zoom out, as this kind of condition on the number of vertices and the number of edges, or the fact that if you remove any edge, the graph becomes disconnected. Okay. Okay, so let me give another, oh, my yellow seems to have run out. Okay, let me give you another characterization of this. So another, characterization. So an embedded cycle in a graph G is a cycle with no repeated vertices, except for the first and the last. Okay, so of course the usual picture that you can kind of imagine is that you have a graph, maybe it's more complicated than this, something like this, and then a cycle, an embedded cycle, a usual cycle is allowed to retrace its steps. An embedded cycle just says you can go around without ever retracing your steps until you hit the last one. Okay, first and last are the same. Okay, so notice here that if you have, if there is an embedded cycle in a graph G, okay, then removing an edge from that cycle does not disconnect the graph, removing an edge from a cycle, from that cycle, does not disconnect G. Okay, so let me just draw kind of here's a kind of the cycle that you see. Here's my favorite edge. Again, it's part of some more complicated graph. So I don't really know what it looks like over here. The claim is that I take any two vertices. So if I take V and W, I should be able to connect them. So they are connected by a path in G. Again, I always will forget this, but I should say a connected graph. If it's already disconnected, that doesn't help. Okay, so V and W are connected by a path in G. Then we have to show that V and W are connected by a path in G minus E. Okay, so I don't know, here's my V over here, here's my W over here. I draw this path which potentially could go through V and W. And then the only thing to note is that since I have an embedded cycle, if I want to avoid E, so this would show that G minus E is connected. If I want to avoid E, I come to here. This path is problematic because it passes through E, and so I just use the rest of the embedded cycle to go around. So this gives me, if you want, just an alternative way to cross between these two vertices. That means I can get to V and W without using any of the edges in the embedded cycle. I mean, not using E in the same argument works for any one particular edge. Okay? So another way to say this, then, is that a tree, so T is equivalent, or maybe I should say a graph is a tree exactly when it has no embedded cycles. Okay, so in other words, the picture that we have, connected graph is a tree if it has no embedded cycles. The usual picture that we have now of what a tree can possibly look like is accurate, right? The key thing, if you're kind of drawing the picture, is that you don't see any loops that you can just cycle around. Okay? Okay, so a leaf of a tree, let's say, I guess the definition, a leaf of a tree is an embedded, is a degree 1 vertex. Okay, so in this picture, maybe I'll draw them green because, make a nice tree. All of these are leaves. The number of leaves can kind of greatly depend on the number, on the particular tree, not just the number of vertices. So let me point out, there's kind of a maximal amount of leaves you can have, where if you have a single interior vertex, this is sometimes called the star graph. So you can have, in general, n vertices and n minus 1 leaves. Okay. It's pretty easy to see that you can't have n leaves because then every vertex would have degree 1. Okay. On the other hand, you can have a tree. Maybe here's the kind of opposite spectrum, which you have a graph here with n vertices. It's a tree, and it only has 2 leaves. Okay, so here. So the line graph can have n vertices and 2 leaves. Okay, and in general, you can draw some pictures to convince yourself that any number between 2 and n, or n minus 1, is a possibility. Okay? It does turn out, though, that, so here's, maybe I'll say this is a lemma. Every tree does have at least 2 leaves. Okay, so this kind of line graph for a tree is the minimal case. Okay? Of course, if you're allowed to have a cycle, you can have a graph like this with only 1 degree, 1 vertex, but if I removed one of these edges to make a tree, all of a sudden I would start putting in some degree 1 vertices. Okay? So this isn't too hard, so let me just kind of recall that the sum, the sum of the degrees of vertices, okay, so where you add up the degree of the vertex, so the number of edges containing it along all the vertices of your graph, okay, so over all vertices of the graph. The first thing we showed on Tuesday was that this is twice the number of edges. And of course now, since we know that if you have n vertices over here, the number of edges is n minus 1, so you get 2n minus 2. Okay? So this means, so therefore, n numbers, which are all greater than or equal to 1, notice you can't have a degree 0 vertex, because that would imply the graph is disconnected. So you have n numbers on the left-hand side, and they add up to 2n minus 2. So that's essentially the pigeonhole principle tells you that at least 2 of them are equal to 1. Okay? Because if there was only 1 which was greater than, or 1 which was equal to 1, then the sum would be at least 2n minus 1. Okay, so trees are themselves kind of a really interesting and important class of graphs to study. Maybe I'll mention where they kind of, one way that they naturally come from is the notion of a spanning tree. Okay, so this says if you have a connected graph G, so let's say G is a connected graph. Okay. A spanning tree T contained in G is a subgraph, which maybe I'll just, I don't know if I kind of formally said this on Tuesday. Okay, so a subgraph just means that the vertices of T are contained in the vertices of G. That might not be all of them, but and also the edges of T are contained in the edges. Okay, so you're only allowed to connect vertices in T which were already connected in G. Okay, so a spanning tree is a subgraph T contained in G, which, okay, so for one thing is a tree. Okay, and contains all the vertices of G. Okay. So in other words, if you imagine you want to connect up 2 points in G with a path, what this tree is saying is that you could just, since it contains all the vertices and trees are connected, you could just follow this tree. Okay, so for example, if I started, I don't know, with something with the K5 graph, then a spanning tree could look something like this. That's a perfectly good tree, which contains all the edges of G. But of course, there's a lot more. Let me try to draw a slightly different looking one. Here's another spanning tree. Let's see, that should do it. So here, maybe that picture got a little complicated, but that's what that tree is. Over here it's this, just the star graph. Okay, so spanning trees, let me change colors, spanning trees turn out to have a number of applications. So for one way, for one thing, they give you kind of a way to move around your graph in some way that's kind of unique, in the sense that if I take a vertex V and a vertex W here, there's now a nice kind of unique way to move. So it makes a choice on your graph of a sequence of paths connecting vertices. This comes up a number of times in working with algorithms. So often if you want to find, say, an algorithm which gives you a shortest distance path between two vertices, the first thing you do is choose a spanning tree and then kind of decide how these other edges play with it once you add those in. Okay? So kind of notice, of course, there are usually G has many spanning trees, many different spanning trees. Okay. But the theorem, which is not going to be too hard to show, is that, and what makes this useful is that every connected graph has a spanning tree. Okay. And the proof isn't so bad. Let me just kind of give you a little sketch. It's essentially a full proof. Okay, so if, we've shown that a graph is a tree, if every edge is a bridge, every edge is a bridge. So in the sense that if you take this edge and remove it, it disconnects the graph. Okay. So if we start with kind of any connected graph G, we're going to kind of iteratively remove edges. Okay. And the edges that we remove are just the edges that are not bridges. Okay, so if an edge is a bridge, leave it alone. If every edge is a bridge, then it is a tree, so you're done. And so if an edge is not a bridge, just in the first step, so removing one edge, then remove. So we're going to kind of repeat this process. Okay. So what does it mean? Let me call this edge E. So if E is not a bridge, then we remove it. Since it's not a bridge, it means G minus E is connected. Okay. And then we just, apply the same procedure. If every edge of G minus E is now a bridge, it's a tree, so we're done. If there's an edge which isn't a bridge in G minus E, like another one F, then you remove F and you just keep going. Okay, so repeat until left with the case where every edge is a bridge, so repeat until you get a tree. Okay, so for something like K5, you might initially remove, let me see if I can do this with erasing. Let's see. So you can remove this edge, see if there's any bridges. I don't think there still are any, so you can then remove this edge, see if there are edges which aren't bridges. Keep going, keep going, keep going. Now I have a cycle. Still every edge is not a bridge. But eventually I'll just get to the point. I'm forced to get to the point where everything... Oh, let me put writing back. Okay. So eventually you get down to n minus 1 edges, and then you're forced to be a tree. Okay? Okay, so one more kind of combinatorial problem about spanning trees is a really pretty formula by Cayley. So this is called Cayley's formula. In general, there are ways to determine for any graph what the number of spanning trees are. There's not usually a nice formula, or not as nice as this one, but Cayley's formula says that the number of spanning trees on the complete graph Kn is n to the n minus 2. So you should think this is really large. Okay, so even for, say, K4, let me draw it in this way so that it looks, so this is a complete graph on 4 vertices. There are 16 spanning trees. Okay, each one containing 3 edges. Okay, so it looks something like this. Okay, so I should point out here that the formula is only nice if the labels matter here. Okay, so for example, this spanning tree, where if I say 1, 2, 3, 4, I'm counting this as different as 1, 2, 3, 4, even though as graphs, these are both the same graph, right? So this is kind of different for us, for this nice formula. They're not different in the case that you get spanning trees which are the same, in this case just star graphs. Let me point out that the unlabeled case is unknown. So there's no at least nice known simple formula for the number of trees on n vertices where you don't care anymore about the labels, you only care about, where you only care about kind of isomorphism type of the graph, okay, of the tree. Okay, so let me give you kind of a little idea of how to show this. Okay, if we see n to the n minus 2, of course, we kind of know what this should be, right? I mean, where have we seen a formula like this before? Well, it comes from just having n minus 2 slots and putting permutations. So this is n minus 2 permutations of n objects. Okay, so for the for case, we want a way to associate. Oops, that's too many. If I had n equals 4, okay, I should be able to associate to a spanning tree here something like a sequence which will look like 1, 4, where this can be anything in 1, 2, 3, 4, and this is also anything in 1, 2, 3, 4. Okay, so let me kind of give you an idea on how this bijection works. Okay, so one way is you can start with a spanning tree. And we want to produce a sequence of numbers, okay, 1 through n. So this is a spanning tree of Kn. I'm assuming all my numbers or all my vertices are labeled by 1 through n, and I want a sequence of n minus 2 numbers all living in 1 through n, okay? So here's what you do. So first, you start with the smallest label of the leaf. Maybe I'll kind of do it over here for a particular example. Again, these numbers are kind of chosen at random. Okay, so there's my tree, which is a spanning tree for the complete graph on 6 vertices. So the first thing you do is you start with the smallest label of a leaf, which here is 2. Okay, so we're going to delete and then write down the unique neighbor. Okay, so here the smallest label was 2. Now we're going to delete 2 from the picture and write down 5. Okay, and now we keep going. Okay, so 3. Oops. Keep going. So let's just see what happens here. So the next leaf, so the 3, 4, and 6 are still the only leaves. So we look at 3, that's the smallest one. We delete it and write down 1. Okay. Now 4 is the next smallest leaf. We delete it and we write down 1 again. Now remember, repeats are allowed in this. That's why we would have something like 16 possibilities. Okay. Now again, we keep going. Okay, I'm back to red. So notice now, before 1 was not a leaf of the tree, but if we remove 3 and 4, it has become a leaf. So this gets deleted as well. I mean, this is now 1 is now the smallest label, and its unique neighbor is 5. Okay, do it one more time. So now we're just left with the graph on 5 and 6. This one gets deleted. And we end up with a 6 at the end. Okay? Okay, so you're probably going to complain. Well, you can't complain in person, but you can complain to the video that now I have 5 numbers here, and I promised you 4. Well, notice that any way that we kind of possibly did the labels here was always going to end, the last term of the sequence was always going to be 6. no matter where 6 was, now 6 could be written earlier in the procedure. Like that's fine. This number could have started off as 6. That would have been no problem. But we would never remove 6 because it's the largest one until the very end. Okay, or we're always, I guess, left with just the vertex 6. So no matter what happens, you always end with this. So we can delete that picture, or that number from the sequence. And now we're just left with 5, 1, in this case 5, 1, 1, 5, and that's the sequence of 4 numbers out of 6 possibilities that we wanted. Okay? So, kind of strongly encourage you to do this for other graphs, for other spanning trees. Okay, of say K6 or K5, K4, whatever, and see kind of how the graphs determine this sequence. Okay, so to go the other way, so we also want to start from a sequence and then build a tree. Okay, to show the bijection. So maybe one thing to notice is that any degree 1 vertex of a tree, of the spanning tree, never shows up in this sequence. Okay? And actually, you can work out the degree of every single vertex in the spanning tree by exactly how many times it shows up, minus 1. Right? So if I had the vertex 2, the picture is getting a little messy, but if I have the vertex 2, the procedure never gives me a 2 because that's the one, or a 6, 4, or 3, because I'm always deleting the leaf and putting in its unique neighbor. Okay, so any leaf never gets mentioned. This, for example, is one way you can see a tree has no, or it has at least 2 leaves, is because you only have n minus 2 things and n numbers, so at least 2 of the numbers get left out. Okay, so any degree 1 vertex never shows up in a sequence. And then if you also look at the amount of times, let me put this here. So we see 5 twice and 1 twice. That was because each of the because the 1 vertex and the 5 vertex had degree 3. So they both get picked up twice, 1 from 3 and 4, and 5 from 2, and then eventually 1. Okay, so now to see kind of how if we started, right color, if we started from 5, 1, 1, 5, how would we kind of get this tree back? Okay, so you first find the smallest, it's a similar procedure, find the smallest n not in the sequence. Again, there's at least 2 of these just by the number count. Okay, and you attach the vertex to the first number in the sequence. So in our case, you start with 2, and the rule is you go to 5. Okay? And you just repeat this. So you repeat, except you do it for, again, delete the first number from the sequence and keep going. So delete, and write down that unique neighbor. So in this case, you had 5, you found 2, then you deleted 5 and connected 2 to 5. Okay, and then you keep going. So let's just see what this does. So now you're here. The smallest one that you haven't added already is 3. Okay, so you put 3 somewhere. Since it's 1, you attach it to 1. Then you do the same thing. Throw out the 1. Smallest one is now 4. Attach it to 1. Do the same thing. Now it becomes a little more interesting because before the sequence had 5s and 1s, now the sequence only has 5. Okay. So what's the smallest number not in this sequence? It's 1. And you attach it to the vertex that just had 5. Finally, once you've done this, remember there was one more vertex to add, the largest one. And the largest one just gets connected. As we saw, the largest, this is really a sequence with n-1 letters with the largest one always at the end. Okay. And it gets attached to the last vertex of the sequence. Okay. Okay, so I would, kind of as an exercise, do some more examples where 6 is not a leaf. Of course, you can just relabel them to see kind of what sequence you get. So something like, if you put 6 here, 1 here, or I don't know, maybe make it a bit different, 3, 4, 1, 5. Okay, what's the sequence that you get? You get 4 numbers. Again, always ending in 6, or 5 numbers, which always end in 6. Okay, and then from those, you can go the other way. Okay, so that was essentially all I wanted to say about trees. It's a really, again, this kind of Cayley's formula is a very pretty combinatorial formula. And maybe at some point I'll talk about other graphs. Okay, but now I want to kind of go to the next topic, which is graph colorings. Okay, and we're going to mainly see vertex colorings. There's also an idea of edge colorings. Okay, so what is this? So G is, again, it's usually convenient to have it be a connected graph. Okay, so a vertex coloring of G is an assignment of a color. So assignment of a color to each vertex of G so that adjacent vertices don't have the same color. So adjacent vertices have different colors. Okay, so there's kind of 2 things that we'll ask. So you can always ask kind of what's the minimal number of colors that you need. Okay, so of course it depends on the graph that you choose, and it's tricky, but it's an interesting question to ask if I have a certain graph or class of graphs, what's the minimal number of colors that I can use? Or you can also ask if you have k colors to choose from, and let's say you can do it, okay, kind of how many different k colorings are there? Colorings are there? Okay, So let me just kind of draw an example first that maybe there's kind of two very silly examples, but everything kind of oscillates between those. So the first, again, I did say it was a connected graph, but if I had a graph which was just a bunch of vertices, the reason why it's connected is the more interesting case is because if it's disconnected, you can just color with all the same color, if it's just a bunch of points. And if it's, on the other hand, a complete graph, it's pretty easy to see that, well, if I have this one red, nothing else can be red, so this next one has to be green, this next one has to be blue, this next one has to be some sort of other blue, and okay, this one has to be black because I'm running out of colors. Okay? So for Kn, so let me give some notation. So chi of G is the smallest K, so it's called like the chromatic number of a graph, so that G can be colored with K colors. Okay, here the chromatic number, or the coloring number of the complete graph Kn is just n, the number of points. So this one had chi equals 1, okay? It's not so hard to convince yourself that if you have any tree, this is 2. So you only, no matter how kind of complicated your tree is going to be, you can always just kind of get away with only using 2 colors, red and blue. Okay, so why can you do this? Well, let me just kind of, essentially the argument is that you just do it and you don't run into a problem. So you pick a vertex, say that one's red. It forces, once I've made a red choice, all of its neighbors are forced to be blue. Now we want to do it in 2 colors, so that means that all of these ones are forced to be red. And I guess in the picture I drew, that's almost out. And then the neighbors of those are forced to be blue. Okay? The reason this works is because there's no cycles where you can have an issue. So if I tried to do this on, say, a pentagon, so just if I kind of naively did the same thing, I would say this one is red. Its neighbors are blue. Oops, I guess I don't need to write that. Then if I was trying to do it with 2 colors, I would say their neighbors are red, but now because I have a cycle, I've kind of come around in 2 different ways, and now this edge is bad. Okay? Now, it's trickier than just that, though. So let me say, like, if I did the same thing with a hexagon instead of a pentagon, I could say, well, this one is red, neighbors are blue, their neighbors are red, and the last one, since I only have 1 left, I can say this one's blue. Okay, so it's not just being a cycle. There's a difference between being an odd length cycle, and being an even length cycle. In the tree case, there's nothing to worry about because there's no cycles. Okay, so you just pick a vertex and go. Okay. In general, a bipartite graph is just another way of saying that the chromatic number is 2. What this means is that your graph looks like a bunch of red vertices which aren't connected, and a bunch of blue vertices which aren't connected. And then there are some, here there's a lot of flexibility. I don't know when I'll stop, but just give 1. Okay. So the important thing is that there's no edges kind of over on these sides. All the edges just cross from red to blue. Okay, so you get a lot of graphs that way. So where this comes up, kind of one example slash application, or how you can think of these types of problems, is imagine that you're trying to schedule tasks, 1 through n. So maybe, I don't know, there are, or maybe tasks or meetings, something that has to take place, or classes on a calendar. That would also, on the academic calendar, that would work too. Okay. You can make a graph if there are conflicts, something like time conflicts. Okay, so maybe one class runs at the same time as another class. The chromatic number of this graph is the minimal number of time slots needed. Okay. Because again, if two things here are the same color, that means that they're non-adjacent. That means that there's no conflict between their times. On the other hand, if they're adjacent, they have to be colored differently, so they have to be given different time slots. Okay? All right, let me say kind of typically, finding the actual value of this chromatic number, this is oops. This is very hard to compute. Because, I mean, you can think it's reasonably simple to give upper bounds. Like if I wanted an upper bound on the chromatic number, all I have to do is find some coloring, which I can, you can use a lot of colors to do that. On the other hand, what's tricky is if I hand you a graph and, you have to determine, can you color this graph with 5 colors or whatever, it's hard to work out because there's a lot of different possibilities for the colorings. Okay. So maybe I'll give an upper bound that does always work. So this one, again, is kind of the simpler direction. Okay. So the chromatic number is always less than or equal to the maximum degree plus 1. Okay, so this is overall vertices of your graph. Okay, so let me just, I don't know, here's some toy graph. And let me label the vertices. Oops. So here's 1, 2, 3, 4, 5. Kind of chosen at random, hopefully random enough. Okay. And so you have your colors. So let me say it's more convenient here to think of your colors as kind of oriented. So let's see, the maximum degree of any vertex in this graph is 4. Okay, so the claim is 5 colors work. Of course, here you can check that it's not, probably 4 colors also work. I haven't checked it, I guess, but I would imagine 5 isn't the upper bound that's actually attained, but it's just what you're kind of always given. Okay. So let me just make an ordering of the colors. So I have red is kind of smaller than green, smaller than blue, smaller than the other blue, smaller than black. Okay? What this means is that if I have a choice in colors, I'm going to choose to do red first. Okay, so now you just go to your vertices. You start with the smallest vertex, and you color it red. Then you go to your next smallest vertex, which is 2. And there's no, so far there's no constraint on what 2 can be. So you again make it red. 3, you do the same thing. There's no constraint on what 3 can be because none of its neighbors are colored. So you choose the smallest color again, and you make it red. Okay, now you go to 4, your next vertex, and there is a constraint. So you go to your next color, which I just chose to be green. Now you go to 5. The constraint is that you can't do green, but still the smallest color available to you is red. So you do it red. Now you go to 6. You see red and green are both taken, but light blue is available. You go to 7. Red and blue are available, but green is free. Or sorry, red and blue are taken, but green is free. And then 8 gives you the smallest one, which is blue. Okay, yeah, so as predicted, we got 3 colors here. I should point out, so in this case, it is the minimal example. You can, if I have this K3 graph inside, I definitely need 3 colors there. So here, chi of G is attained. Usually, this is not attained. Okay, so it's again, it's a number that in general computing it's pretty impossible, but there is definitely. And I should point out, this algorithm that I just gave for coloring never gets stuck, because you've always taken enough colors so that you'll always have a free choice. Okay, no matter how the various vertices in the previous step are beforehand, because there's only 4 in this picture, 4 colors that could have possibly been taken, and then you might have to add the 5th, but you can't be worse than that. Okay, so I just want to say one more thing. Kind of the next question, which I already asked, was, well, if you have K colors, and K, say, is greater than or equal to the chromatic number, well, how many colorings are there? Okay. So we'll talk about this more on Tuesday. Let me just kind of give some notation first. I'm going to write PG of K is the number of K colorings of G. Okay, so you should think of this as a function in K, or a sequence, which kind of is, you can also think of it as 0 for a while, and then you start hitting where the chromatic number is in your sequence, and then you get some non-zero values. Okay. To see kind of a hint of what you get, so let me do this for the complete graph. Okay, so I need at least 5 colorings. Okay, maybe I should point out that I do view, if you just make a coloring swap where all the red gets swapped with the green, that's a perfectly fine way to color. But we do count these colorings as different. Okay, so here we needed at least 5 colors. Okay, so 5 colors, or greater than or equal to 5 colors. Let's just try thinking about it for 6. Okay, so I want to color all the vertices with 6 colors, and I want to see how many ways we can do this. Well, for this vertex, we get 6 possibilities. For the next vertex, you get 5. For the next one, you get 4. Next one you get 3, and next one you get 2. Because at every edge that you've or every vertex that you color, if you look at the rest of the graph, it's just a complete graph on n-1 vertices. Okay? So in other words, for the complete graph, we get that PG, or maybe I should say PK sub n of k is the same as n permutations of k objects. Okay, so the objects here were the colors that you chose. Okay. That's one example. So at least in the case of a complete graph, we get something which is kind of familiar to us. Let me do another example. Okay, so here, this is just kind of a randomly chosen graph. Okay. Now I notice if I want to count the colorings, let me point out that I have these, this is just a choice, but I have a K3 subgraph right here, okay? And if I have a coloring of the whole graph, I get a coloring of the K3 subgraph, okay? So I can think of this as having K choices for X, K minus 1 for Y, and K minus 2 for Z, okay? And then I have to fill out the whole rest of the graph. So let me give some colors here. So maybe I just chose green, red, and blue, okay? And now I need to fill out everything else. So if I have green and red, notice that this one, can be given any choice of color except for green and red. So let me call this W. So I get K minus 2 choices for W. And once I've made the choice of Z and W, running out of letters, okay, U. Okay, I have K minus 2 choices for U, okay? So in other words, if I write P, this is my graph G, PG of K, once I've exceeded the chromatic number, which is 3, then I get PG of K is K times K minus 1 times K minus 2 cubed, okay? And here's kind of a nice, kind of startling fact, which I'll talk about on Tuesday. So P, it's called PG of K because for any graph, G, the chromatic, counting K colors is always a polynomial. In K. Okay? This should even be a little k. Okay, so this is called the chromatic polynomial of G. And it turns out, kind of curiously, to share a lot of properties with familiar polynomials that we've seen before. So something like the polynomials coming from the choose functions or binomial coefficients or 1 plus x to the n, these chromatic polynomials turn out to have share a lot of similar properties, which I'll talk about on Tuesday. Here, of course, you should think it's a little special case. So it'll take a little more work to show it's a polynomial. What was nice here is that once I determined this coloring, then I knew exactly what this could be, and then I knew exactly what this could be. So there was a bunch of kind of complete graphs which were glued together. In general, it's a little more of an argument, but not so bad. Okay, so again, maybe I should say apologies for missing class, and I'll see you Tuesday, and turn in your homework on Tuesday. All right.